All right, so today we are going to be talking about the class project and the project schedule, which will be updated in the syllabus early next week at the latest. We're going to be talking about the velocity profile for accelerating objects, and it's really important concept when we talk about moving things. And most things are moved by motors, AC or DC motors, and internal combustion engines is the majority of how we move things around. So we'll talk about that, and we'll pause and then get into Scrum, Trello, and then talk about some vendors that you guys will need to use. Okay. So the motivation for the course project is that in order to learn design, you have to do design. And with, we can't just talk about it. We actually have to do it. So if we cover a bunch of mechanical elements, we did the theory and all that, it doesn't necessarily mean you know how to use them. And so only by using them can you kind of know what you don't know and where you have gaps of knowledge, and then be able to make decisions for real parts with real sizes. So when we study the elements, and when we say elements, we are talking about bearing shafts, gears, brakes, etc., springs, screws. It's not the same as, going and finding, an element from a vendor that you can actually use in your design. So one of the things you're going to learn in this class is the background analysis for different components, but really what you have to do at the end of the day is you got to go find something off the shelf, because you obviously are not going to design a screw for a machine in general, and you need to get the economies of scale so that you can buy things that are affordable so that your costs don't explode. And as such, you need to be able to do enough analysis, pick the right components, but then you actually got to go and find those components in real life. So for the course project, you're going to have a bill of materials with actual components and a cost for the real machine. Okay. I have suggested but not required that you use SolidWorks. SolidWorks for an individual costs about $5,000. It's used by the majority of people that are making parts. In fact, it has the largest market share. You can see in this graph right here, the biggest part of the pie is SolidWorks, followed by Inventor, and then others. And then you have Siemens NX, and then you have Creo, which is about half of the users of SolidWorks, and then you have CATIA, Solid Edge, and whatever. So because so many people are using SolidWorks, it is my strong suggestion that you use SolidWorks in your design for this class. The reason is because you may not have time to learn it later, and often in a mechanical engineering job, people kind of want you to have some background in there. So this is the instructions. If you search UNCC for SolidWorks, I do believe that you can install it. Actually, I know you can install it on your machine. You'll get an educational version, and you may not have the time to learn it later. So there's more than enough time to do well in this project and to go up through the learning curve for SolidWorks. So please heed my advice. Go ahead and install it and start to use it, because it may it'll add another tool in your toolbox. Okay. All right. So let's talk about the class project. Okay. So this semester we are going to be designing a machine to lift shingles. Let me just sorry, let me change here to the tablet. So this semester we're going to be designing a machine to lift shingles. So you guys are the Niner designers, and you have a friend, imaginary friend, who asks you to help design a shingle bundle lift system to safely transport shingles from the ground up to a 2-story home, which is usually 18 to 20 feet. The ladder should extend above the roof line, about 24 feet. When I say ladder, whatever device you make. There are cable-mounted systems commercially available. I'll show you those in the link. But he wants you to use a system that uses a rack and pinion. So we're going to have a rack and pinion design for the machine that will carry bundles of shingles up, so you don't have people doing this. And you'll have a full bill of materials list and final cost for this actual project. And you have to design the entire thing in CAD and perform a complete analysis of the design. So what we're going to be going through the semester is defining the structure, finding the loads, and then using the elements that we learn, such as like spur gears, bearings, shafts, and etc., to solve this problem with mechanical elements. So if you follow this link here, you'll find the vendor for this machine. In fact, I just saw one of these in my neighborhood after I had written this up. So last week, so people are using these machines, but they have a cable, and the cable mounted system has to go all the way up and down through the center. So you can be inspired by this and benchmark your design. But what you're going to do is actually pick a different, you're going to design your own machine. Okay. So if I show you this video here, this is these hoist ladders. This is the company, Safety Hoist. And they talked about if you do this, you get large fines. If you have to bring out a crane, it's a problem because it can tear up the lawn. There's not always room. So they've made this clever little device here that is gas powered. For this one, they have an electric version as well, and the brake engages and then engages the thing and the cart, and then it goes all the way up. Okay, so you can watch those. They have a different version, and they actually have an updated electrical version as well, and they have some accessories. I think they're selling them for like $3,000 to $5,000 right now. And usually for commercial products, you want your profits margins to be, for retail, at least 40%. So you can imagine that it probably costs them a little bit over half of what they're charging. Okay, so your task is to design the entire machine from scratch with your 2 project people, and I've tried to kind of lay out the steps that you would need to be able to do that. There's some requirements, such as the machine has to be transported. Obviously, 2 people should be able to move it, so you can't have anything that's too heavy. You ought to look up the OSHA requirements for lifting weights for people, things like that, to make sure that you're compliant or at least informed of what the standards are. You're going to use components that we cover in the class, structure in its static and dynamic analysis. Of course, that's previous course materials from statics, dynamics, mechanics, and materials. And then you'll use a shaft on a motor with keys, possibly couplings, whatever you choose, rolling element bearings to go up and down and retain the structure. You'll use spur gears and a rack and pinion design, some springs to have on the bottom for a soft landing, so if it disengages for some reason that it doesn't destroy the equipment. And then you'll pick the screws, bolts, welds, and analyze the preloads that you expect to see in the bolts, and make sure that the loading conditions will that the welds will hold those loading conditions. This is the end of the semester here. This is earlier in the semester, and so we will be adding information throughout the semester, but there's no reason that you can't start designing the components. Okay, So the first step is to design the cart, just the static analysis that can take 3 bundles of shingles or up to 240 pounds. And at the top, you need to have a mechanism that'll rotate the cart so that it's easier to get unloading off. It's easier to unload. So you need to analyze the loading and deflection for the cart and the structure that will hold it. So the first step is just make sure you really understand everything. Understand, how the loads are what loads you expect to see and the thing. And really what you care about is the worst case scenario, right? Which would be the cart in the middle that would cause the greatest load, or near the middle, depending on the angle, on the supporting structure that you choose to go from the ground to the roof. It'll cause bending. The bending will cause bending stresses and deflection. And you should be able to do the analysis for that and get some general sizes. You have to use EES to do your design so that you can play around with the variables and see how that changes the sizes of things. So even though we don't cover all the elements, you should still be able to sort of, draw the design and the concepts and the components where you think they'll be. And then later on, we can do the analysis, and if they're too big or too small, we can change their size. Or we can go ahead and swap them out. But really, I want you not to overthink it and think if you have things that are rolling, you're going to obviously need bearings or a bearing surface, etc. And then you'll put these concepts in SolidWorks. We already talked about that. And then simulate the loads that you expect in your CAD package. And you can do a simplified loading condition and make sure that they match your analysis, okay? So we're talking just simple, big picture, back of the envelope, engineering style to make sure that you're in the right neighborhood. So then you can move on to designing the structure, including selecting material and analyzing the deflection. Try to keep your deflection less than 1 inch for the latter portion of it. You should be able to do the conceptual and embodiment design in order to start defining things in CAD. Okay, you should be able to get all your weights, select the structure, and figure out how you want to connect the cart to your rail system so that you can use a rack and pinion structure. You won't be designing a motor, but you'll design the requirements for a motor and transmission. You will design the gearbox, at least for like the gear ratios, and I would like you to do the analysis for those using spur gears that will ride along with the cart and provide the input power necessary to drive up the rack. So you can think that on the cart you're going to have a motor and a transmission or gearbox that will be connected to the shaft. On that shaft you'll have a spur gear. That spur gear will run along the rack for it to go up and down. Okay, but this is the thing with design is you got to pick all the sizes and the shapes and then make sure they don't break. So we're going to be covering all that in this class. The motor is sized from the desired acceleration, velocity, and position curves. Usually we'll start off with the acceleration. That'll allow us to determine how much torque we apply, and we'll be talking about that today. We'll talk about some more of that. You can reference the slides later for this information. You'll pick the bearings, springs at the bottom of the cart or at the bottom of the ladder to soften the landing if it gets loose and falls so that it doesn't ram into the ground. And then you'll design the welds and fasteners and some mechanism for safety for the brake that will clamp to the structure. And that can just be as simple as, brake pads with a known friction between materials, and then determine the required normal force to prevent it from sliding down. Okay, so by the end of the semester, you will be completing the calculations and do the paper analysis, as I say, sort of This will be your EES file that has everything in there that allows you to size everything properly and make sure that nothing's going to fail. And you'll have to have a complete SolidWorks assembly and then a CAD static load analysis with the deflection to compare to your calculated values, then a bill of materials and a complete report. You have to have bill of materials with suppliers, and I will be giving you links for where you can find stuff. Okay. The schedule I have to update here, so I'm not even going to show it because I have to make sure that what I ask for a deliverable is stuff that we've actually covered and flesh out the details of the schedule. So I owe you that, and I'll get it to you early next week. Okay. So that is the project that we're doing this semester. Okay, that's the class project. And now we need to talk about how do we size the motor. Okay, so we size motors based upon the required torques, and we know from dynamics that the sum of torques is equal to I alpha, where I is the mass moment of inertia. And so if we want to pick a motor will tell us what torque we have, but we need to know the desired acceleration, and we need to know the I, which will be related to what the motor is driving, the shaft and the other things that are connected to it. So once we have the mass moment of inertia, we know our desired acceleration, then we should be able to pick the selected torque that we need for the motor. Now, the torque can be changed with gearbox. Okay, the power that you need for your system cannot. The power that you need for the system is the force times the velocity, or the torque times the angular speed. Okay, and that angular speed is going to be coming from how long you want it to take your cart to get from the ground to the roof, or those 20-25 feet that it's going to be traversing. Okay, so and then what's typically done is then you have some motor, and in this case we'll have some form of servo motor, or motor that can that is not just on or off, or has a soft start or soft speed. You can look into those details, but if we sum these torques equal to I alpha, then the torques on the left hand is going to be the torque supplied by the motor minus the load on the shaft, okay, that we're going to be experiencing from gravity, and then it's going to have to equal to I alpha. So if we can define the geometry of what the motor is driving, then we can find the size of the motor that we need for this. Now, when you send a command to the motor, what is often done is this profile here. Now this is called the trapezoidal velocity profile. Okay, so the black line is your velocity. So usually people want to go at a increasing velocity up into their desired velocity, and then hold that velocity until they want to stop, and then they go down. What that means is that in the beginning we have a constant acceleration. Okay, now if we integrate this acceleration, we'll get this velocity, and if we integrate that velocity, we'll get this position shown in blue. And this is your typical velocity profile. Okay, so what you're going to have to do is you're going to have to say, how fast do I want my cart to go? How long do I want it to take to get from the bottom of the ramp, the ladder, or the structure all the way to the top of the roof? And that'll define this. And how fast do I want it to get up? How long do I want it to take to get up to my desired velocity? So then you can pick, based on those numbers, the desired acceleration, and then from the load that you are going to experience on the shaft and the shaft's moment of inertia, you can pick the torque that you need for that motor. Okay, so now this is only the case when it's going up, right? Because when you're going down, gravity is your friend, and so you don't need that. You'll have to be able to have enough torque to support the weight of gravity and the load. But if you get it going up, you won't have any problem with it going down. You just have to be careful that you size it appropriately. Now, This is often called your SVA diagram, S being position, V being velocity, and A being acceleration. Okay. Now, the problem with this profile, though, is that when we take the derivative of something that goes from 0 to a non-zero value in a infinitesimal amount of time, then we actually have a discontinuous function. So if you look here, we have the position, you integrate the position, you get the velocity, integrate the velocity, you get the acceleration. I'm sorry, if you take the derivative of the position, you get the velocity, derivative of the velocity, you get the acceleration. If you take the derivative of the acceleration, you get jerk. And that these transitions where you go from 0 to non-zero acceleration, and then from non-zero acceleration to zero acceleration, if you take the derivative at these points, you get these huge spikes in your machine due to jerk. Okay, so jerk is the derivative of the acceleration, and if you don't have smooth acceleration profiles, then you'll get these harsh inputs and jerk into your system. Okay, now the derivative of the jerk, I kid you not, is the snap. The derivative of the snap is the crackle, and the derivative of the crackle is the pop. So if you guys are old like me, you remember snap, crackle, pop from Rice Krispies. So if you forget it, just think after the jerk, there's some Rice Krispies, okay, for the higher derivatives. But we mainly are concerned with the jerk because these spikes in the derivative of the acceleration can cause premature wear, and they're just really not nice to your machine. Okay, you have to love your machine, you have to be kind to your machine, you have to take care of it. You have to feel it. If it hurts, you should hurt. Okay, so you don't want your machine to be abused by bad trajectory profiles. Okay, and so what's often done is people use S profile, which is a software profile. For this class, I'm not asking you to get into the profiles. You can use the constant acceleration to size the motor, and then you just buy a motor that has an S profile. Okay, that's the simple way to do that. All right, so what they do with the S profile is they just soften the acceleration. They ramp up the acceleration instead of going from 0 to acceleration. Okay, so this is what's done in a lot of more recent machines versus the older trapezoidal velocity profile that I just showed on the previous slide. So you can soften it up, but what I said is you can design using this case because it's easier to do the math. It's not necessary to go into all these details, and you just do this analysis, but buy a motor that has this profile. Simple enough. All right. This is a picture of the difference between a soft profile and a not soft profile. And obviously we're not advocating for drinking bubbly yellow beverages, but it is a good example of how the different trajectory profiles affect the input excitations into machines. Okay, so you can see with the S-curve as well, we actually are able to get there a little bit faster. It'll obviously depend on the details of the tuning, but some motion controllers are jerks, so just be aware of that. But to do the analysis, you can just pick the desired acceleration. Okay, hopefully I've made that point clear. All right, so for the project schedule, as I said, I'm still working that out. So I will upload the syllabus. The dates may change for the due dates and for the homework dates, so please be patient with me at least until next week, and then you can be upset with me. You will need to fill out a report, and your report will follow a specific format, but I've made it easy for you to do that, to follow this format. Okay, so if you look over here, this is the project report specifications. Okay, basically you need to write a narrative report. When somebody reads your report, it should be interesting. Once upon a time there was a problem, I had a friend, he needed help, we designed this machine, it's awesome, these are the features, this is how we did the analysis, don't you think it's amazing? So, but of course we can't say that in professional work, and so we title it different titles. Okay, And I'm going to skip down here to the contents. So simply, you need to have an introduction, background research, that you benchmarked it, you looked at other designs, you were inspired by this or that. These are the concepts that you found, blah, blah, blah. Goal statement is like, hey, what are we going to do as a team to get this project done? Task specifications, and it doesn't have to be crazy, right? It just has to be like, okay, we need to do this, do that, and do the analysis, define the structure, define the cart. This is how we did it. Describe the design, and a lot of this stuff is going to come straight from what I already gave you. And then you are getting into, how did you solve this problem? What did your solution look like? And conclusions, like, did we do a good job? Are we proud of it? What did we figure out? What would we have done different, etc. And then I want to see your CAD model, which you'll upload with this, and then any supporting files that you think we might need. And just to make it easy, I wrote down what I should see from each one of these sections. And I will not be crazy rigorous. I really just kind of want you to do a sort of informal, good work. Okay? Informal good work. Okay? And these are the guidelines. Okay? So if it's sloppy or you're missing stuff, obviously you're going to lose points. And you're going to turn this same report in 4 times. Okay? And it's going to get better and better and better throughout the semester. So we don't have to do different reports. Fill in what you can for the first one. The first design report update, which we'll put on the schedule. Fill out what you can for the second one. Hopefully most everything is done by the third one, and then at the end of the semester, when you turn in the final thing, there shouldn't be a lot of work. I've designed the semester so that you should never have, a sense that, you have too much work that you can't get done. Okay? And then you're going to, when you do your report updates, what you're going to do as well is you're going to upload a short video, and that short video it will just be your design update, and your peers are going to review you. I think I have that in here, so we'll go back, and I'm going to give you a presentation template for the team presentation. Okay, so you'll have this. This will be your presentation. Okay, you have your team name, the members of dates, and then you just go through the same sections. Okay, so each time you update, so this is the same information. So your slides are really just going to be like a quick snapshot of your report. You'll record it, and then for each person will grade 4 other teams to try to keep it reasonable. And then I have reserved the right to override the grade. Okay. So this is what we just talked about. I'm not going to read it again because I just talked about it. Let me know if you guys have any questions about that. Okay, so why am I having you review your peers' design for these design updates? Well, for 2 reasons. Number 1 is you can copy them if they have a good design. I mean, not copy them, but and be inspired by them. I mean, as engineers, there's really there's an infinite space to solve problems, but in reality, there's classic solutions that we use. And their design can inspire your design, your design can inspire their design, and both of your designs can be a little bit better. Okay? So even though you don't have an awful lot of experience, it's good to review the design and just, play your hand at it. Like, hey, I don't think their numbers are right. I don't like this. Why didn't they do it this way? And the point is really to help people do a better job. Okay? So design reviews aren't meant to be, make you feel like you're an idiot. They're to help you do better work. Now, engineers, in general, we always have something to say, and we can complain just about anything. It's very rarely that we say, "Oh, this is a perfect product." So, take your knocks and then make it better. So that's the whole point. You don't have to have a bulletproof design in this class in the sense that you have the most amazing solution and I'm going to grade you based on that. All I really want to see is, like, can you take the fundamental principles that you have been studying for the last 3 or so years and use them to make a simple machine that solves a problem that you're confident you could go out there and buy the components and make. Okay, so for some of you who have more hands-on experience, this might be a little bit easier. For some others who have never kind of put it all together, at least in my class, you're going to put it all together. Okay, so just put yourself out there. So don't fight it. Just do it and let people help you make it better. All right. So I'm going to pause the lecture here, and then we're going to go into Scrum.